Good morning, everybody, and welcome to the first session of the Grid Operation Seminar of 2023. It's my pleasure to announce our today's speaker, Emma Willett. She's a PhD student at Birmingham University, supervised by Andrea Miglio from Bologna University and Bill Chaplin, who is in Birmingham. She started her PhD in 2019 and will finish the summer of this year. So, and Emma just told me that she might be interested in if somebody has a postdoc, please let her know, because she's still searching. She's on the job market. The topic of today is the Milky Way helium enrichment constrained by red clump stars, and by chance, I'm always excited. So please, Emma, enlighten us.
Thank you. Good morning, everybody. I'd obviously like to start by thanking all the organisers of this wonderful series of seminars for allowing me to give this talk, which, as Paul said, will be about helium enrichment in the Milky Way and our attempts to constrain it using red clump stars. So I'm sure it's really unnecessary to convince anybody here that stellar ages are really important, but they are the fundamental motivation for this work. So whether you're interested in fundamental stellar physics or searching for solar twins, or whether you need precise ages for young stars in order to put a chronology on the formation and evolution of exoplanetary systems and protoplanetary disks, or whether, like me, your main interest is galactic archaeology, in which case the ages of young stars provide you with the clock by which we can understand the chemical and dynamical history of the Milky Way. We really like stellar ages, but unfortunately, they can be quite hard things to get a handle on. So there's really only one star for which we have a fundamental and precise measurement of the age. That's the sun, and we got that from measuring the ages of rocks in the solar system, which unfortunately is not a method which is available to us for any other stars, at least not yet. So in this excellent review from 2010, age determination methods are divided into these three categories of fundamental, semi-fundamental, and model dependent. And the semi-fundamental ages are ones where you have to make assumptions about the underlying physics, but the age determination at the end is not very sensitive to the details of the assumptions. So you can be pretty sure that your ages are going to come out about right. But unfortunately, they tend to have very limited scope because in general, these methods can only be applied to very particular kinds of stars, and often the measurements that you need to make are really challenging. So in general, what that means is that pretty much every stellar age that we might interact with is model dependent in some way. And that means that we're open to all of the many questions and current challenges in stellar models. So everything from what physics you put into your model and how you characterize it, to how you can verify your models with observational tests and constraints. And also, of course, figuring out everything you need to know about the star or stars that you want to model. And that's really where the area that we're looking at here. So particularly the chemical and specifically the helium abundance is what's important for us today. So as I said earlier, my main interest is galactic archaeology. Ages of low mass stars are really important in that kind of work because they can be long-lived and therefore you can probe all epochs of galactic history. But helium abundance is a big problem because we can't really see the helium spectral lines. So getting a constraint on the helium mass fraction Y is a real challenge. Normally, therefore, when you design a grid of models, what one would tend to do is assume an enrichment ratio between helium and metals, heavier elements. And that's basically a way of characterizing the history of galactic chemical evolution. And normally that's just chosen to be one linear relationship. So we have a helium to metal enrichment ratio, delta Y by delta Z, and then we can measure or infer Y from the primordial helium abundance, which we have a pretty good handle on from Big Bang nucleosynthesis, and the metal mass fraction, which you can obtain spectroscopically. But there are lots of open questions about this. There is a whole range of methods for attempting to constrain delta Y by delta Z, everything from studying clusters to broadening in the main sequence of K-dwarfs, and now more and more work on understanding the glitch that you see in astroseismic signatures from helium ionization regions within stars. But all of these different methods can give us quite different answers. So normally we would say that delta Y by delta Z is somewhere around about 2. But a quick search of the literature and you can find answers which cover an order of magnitude from 0.5 to 5. And that's kind of a big problem. I haven't really got space here to list all the many previous works, but this website is a nice summary. It hasn't been updated very recently, but it's a good place to start if you're interested in different methods of constraining helium abundance. So how much does this actually, before I discuss how much this actually matters, we also should ask the question about whether a single linear enrichment ratio is really the right way to characterize all of the galaxy's helium enrichment. So in the literature, there are a couple of open questions which come up again and again, regardless of which method you use, particularly in a plot of y against z, where then delta y by delta z would be the gradient that you would expect through here. In many cases, we see an increased scatter below about solar metallicity. And also, if you fit a line through this data, you would recover a primordial helium abundance, which is far below what we know to be true from Big Bang nucleosynthesis. So these are also open questions. Now, how much does this actually matter? Well, the Breton and collaborators in 2014 did some really nice work where they went through all of the, or many of the open questions in stellar models and tried to quantify the effect that that has on the age of the model at the turnoff. So these three gray bars are the ones that are relevant for the discussion today, and they show the effect of decreasing the helium abundance from 0.28 to 0.25, or increasing from 0.28 to 0.31, or increasing the enrichment gradient, the enrichment ratio from 2 to 5. And you can see that in this axis of fractional age, you can very easily change the turn-off age of your star by tens of %. So it's a very significant effect. And these are not wild changes to be making. This is really quite conservative. And the range of stars or range of masses where this matters is this region of, around about solar mass, where we're really interested in these stars for galactic studies. So in the era where astroseismic ages are really pushing to the 10% precision level, this is definitely an important effect. To give you some context, what this looks like by the time you reach the core helium burning phase for a roughly solar-like star, a change in the helium abundance from 0.25 to 0.28 is the difference between a 15 gigayear-old star and a 12 gigayear-old star, and that's quite a big effect. Also, what you can see here in the red clump portion of the track, the core helium burning phase, is a shift in luminosity. And that's what we're going to be using in this work. That's our proxy for helium abundance as we attempt to constrain it in the red clump. So the reason that this works is that for true red clump stars, so those that have gone through the helium flash, we're not interested in the secondary clump here. They have low mass, and therefore they have a degenerate core during the first ascent of the RGB. And the core degeneracy means that the helium ignition is delayed by very efficient electron cooling until the core reaches some critical mass. And that critical mass is only very weakly dependent on the total stellar mass and the metallicity. And that means that all the stars in the clump have a very similar core mass, very similar central conditions, and therefore a very similar luminosity. And that's really the origin of what we normally think of as the red clump being this observational overdensity on the HR diagram. But it also means that for stars where we have a handle on the mass and the metallicity, the small remaining changes in luminosity are basically driven by the helium abundance. And that gives us an opportunity to use the luminosity as a proxy for the helium abundance. And that's what we're going to try to do in this work. So to do that, we've compiled a sample of Kepler oscillators from the U2018 catalogue, which includes evolutionary state determinations, which can isolate the core helium burning stars from those on the first ascent of the RGB. And then we make additional cuts in delta nu to try and remove the secondary clump. And you can see that's kind of what we're doing here. So the green stars here are what is left in our sample. We can use the stellar parameters, particularly in our case, the mass, either from the evolutionary state corrected scaling relation values, which are given in the U catalogue, or we can determine them ourselves from Param, which does a Bayesian comparison with grids of models to give you your stellar parameters. And we combine that sample with abundance information from Apogee 2017, DR17, and then very precise luminosities based on the Gaia parallaxes. And out of the stars which survive this cross-match from the U catalogue, there are about 10,000 of those. We select about 3,000 to be our red clump targets. Some of those drop out in the course of the analysis, but we always have more than a couple of thousand left, and that represents a significant step forward on previous studies of helium enrichment in field stars. So once we've collected our data set, we need to compare it to a grid of models in order to make this connection between the luminosity and the helium abundance. So in order to do that, obviously, we want to build a grid with no assumed enrichment ratio, no assumed delta Y by delta Z. So at each position in mass and metallicity, we compute tracks in several different helium abundances, which is what you can see here for a solar mass and solar metallicity star. And again, we see the effect of increasing the helium abundance from 0.25 up to 0.34 is mainly an increase in the luminosity, but there are other effects as well, particularly the fact that the shape of the track is changing from quite an acute corner here to something a bit broader in this higher helium abundance track. These tracks also don't show us how much time the star spends at each of these phases of evolution, how much time it spends at the low luminosity phase compared to how quick the evolution towards high luminosity is as the core helium burning phase ends. So in order to try and characterize that, because of course we're much more likely to observe a star at the point on the track where the evolution is slowest, we can assign a fractional age from 0 at the start of the red clump evolution to 1 at the end, and we make uniform samples in this fractional age, so then we generate most samples where the star spends the most time. That looks something like this. So now you see the luminosity distributions for the same 4 tracks, which are strongly peaked at low luminosities and then have tails towards higher luminosities where the evolution is more rapid. But again, we can see the fact that the shape of these distributions changes between the 4 tracks. So to give you an example of how this compares to the observations, we can take the stars which lie in the region around 1 solar mass and around solar metallicity, and we take the median luminosity of that population, and we do that lots of times for many realizations of the observed population, and that produces this kind of histogram. So we're not expecting this to be the same shape as the one from the models. It's not really a like with like comparison. This is just the best visual example I've found that can show how these things compare. So we find that for a population of stars, 1 solar mass and solar metallicity, the luminosity lies somewhere between the models at 0.25 and 0.28 helium abundance. And therefore we can say that the helium abundance of these stars should be somewhere between 0.25 and 0.28. We can then extend this method to bins of lower and higher metallicity. And now, although all the tracks move in absolute luminosity, the important thing is that the observations move relative to the models. So here we see at lower metallicity, a slightly lower helium abundance through to a higher helium abundance at higher metallicity. And this is the observational signature of the helium enrichment in the galaxy. And of course, we also extend this to more bins in metallicity and also several bins in mass, and you see the same sort of effect going on. But what we would really like to try to do is go beyond binning up the data and making these kinds of comparisons, particularly because in the analysis, we found that sometimes we can be a bit sensitive to exactly how we're doing the binning. So what we're working on now is finding a way to do this on a star-by-star basis. What this means is trying to keep hold of the information about the evolution towards high luminosity. So to go back to these, the shapes of these distributions are not the same even within a single bin in mass and metallicity, and characterizing them is difficult, and we don't really want to throw the information away about the shape of this distribution because that contains all the information about the luminosity evolution of the star. So instead, we're using a Monte Carlo technique to try and be non-parametric, if you like. So here you see the luminosity samples for 4 of our tracks against their 4 values of helium abundance. And we can see from the models, and it's motivated by the theory a little bit, that we expect a linear relationship between the helium abundance and the luminosity at a given fractional age. So what we're doing here is taking all the samples at 0 fractional age and fitting a line, and all the samples at a fractional age of 0.1 and fitting a line all the way through. So most of our lines are in the region where the evolution is slow and the gradient is a little bit steeper. And then as the evolution towards high luminosity proceeds, we get a few cases with a flatter gradient where you're at the high luminosity end of the track. And then what we do is take our observed star, make realizations of its mass and metallicity, and interpolate to the appropriate point on the model grid for each of those realizations, generate these lines, and then make a comparison of our observed luminosity to these lines and read off the helium abundance, basically. And what we come out with is a distribution in helium abundance for the individual stars. Excuse me. And we think, well, great, this looks reasonably symmetric. Probably we can use some summary statistics to characterize this. The mean or the median would probably work well. And then we'll just whack it all on a plot and everybody's problems with helium abundance will be solved. Of course, it isn't quite that simple. In many cases, we find stars where the distribution looks significantly less Gaussian. There's a lot more spread, and these stars belong to regions of the grids where the relationship between the luminosity and the helium abundance is not so strong. So it can't provide equally strong constraints for all kinds of stars, all kinds of red clump stars. And also we find a lot of stars where we have a strong peak, but then a very long tail towards low helium abundance. And this is not unexpected. So what's going on here is that to take an example of a star with luminosity in this range, we are most likely to observe a star of this luminosity if it has a helium abundance of 0.31, because this is the slow phase of evolution. However, there is a possibility that it could be a star with helium abundance of 0.28 in a more rapid phase, and an even smaller chance that it has 0.25 in the most rapid phase of evolution. And that's what gives us this asymmetric distribution with the long tails towards low helium abundance for our high luminosity stars. And that's important information, of course, that we don't want to throw away. So if we do make a plot with the summary statistics, this is a very, very naive look. So we take the median of our distributions and we plot Y, and then we can calculate Z from Y and the metallicity. We come out with a delta Y by delta Z, which is somewhere between 1 and 1.5. But we're still really working on how we can make best use of this distribution. So one of the ways that we're exploring this is by using a mock data set. So we use our grid of models and we interpolate across it to produce mock stars with masses and metallicities which match those in our observed population. And we're just making a rough estimate of the uncertainty on the luminosity as a constant fraction. And in this mock data set, we can put in any helium enrichment relationship that we like. So what we're using here is delta Y by delta Z of 1.5 and a primordial helium abundance of 0.25. And that's the green line. The black points then are what comes out if you apply the process that I've just described to you. And if you try to make a simple fit to this result, we find that we systematically underestimate delta Y by delta Z, basically because of this increased scatter in the upper envelope, which is driven significantly by these long tails for the higher luminosity stars. So we have a strong peak for these higher luminosity stars at higher helium abundance, but actually they belong somewhere down here. And this is because it's in the tail of the distribution. So we're exploring methods at the moment for how we can make best use of all the information that we've got. And you can see that these distributions don't look that dissimilar. So, for example, the lower envelope of this cluster of points here actually does provide quite a good estimate of the enrichment ratio that we put in with our mock data. So we may be able to use that in some way. I'm also testing methods with using MCMC to maximize the KDE of all these points, or to use the individual samples and their KDEs rather than just reverting to the median summary statistics. And I think it's possible that the way we'll go in the end is to use a hierarchical Bayesian approach, but this is definitely still an open question. And if anybody has any ideas, that would be great. We can also now at this stage start to bin up the data again, because if we make a group of stars of similar mass and metallicity, but with enough of them, then we should be getting a reasonably good sample across all the fractional ages. Then we'd be making the most of the fact that we have a larger population of stars than has been available in previous studies. And that's also a possibility. We just, of course, have to be very careful that the result that we come out with is not too sensitive to those bins. Some things, however, are definitely encouraging. Looking back to the plot from the literature from Casagrande that I showed at the start, we don't seem to have the same problem with recovering very low primordial helium abundances, at least not for most stars. Any kind of line you draw through this is going to have a primordial helium abundance which is not below 0.2. So that's definitely good news. And it is possible that some of the scatter that we see at low metallicity does come from a physical origin, the same as has been seen in the literature and not really explained yet. It might not all be driven by what we introduced during our analysis. So that is more or less where we're up to at the moment. I wanted to say a couple of words on the Gaia luminosities. They are really the thing that make this possible. So we need high precision luminosities in order to be able to see the difference between the model luminosities at different helium abundances, basically. So we need 5 to 10% here in order to tell the difference between a star with a helium abundance of 0.25 and 0.28. And that's exactly what Gaia provides for us. So this is, of course, a very wonderful tool. But it does have its drawbacks, because when we're using the luminosities with such precision, sorry, I'm in somebody else's office and I don't know how to hang up the phone. Okay. Yes, when we're working with luminosities with such high precision, it does mean that we're sensitive to the 0-point offset on the parallax, which I'm sure everybody here is already familiar with. So in black are the distributions of helium abundance for the 3 stars that I showed before. And in this work, what we're doing is using the recommended correction from Lindegren to the Gaia parallaxes. But if we don't apply any correction, we can see this red distribution. We would come out with a measurably different helium abundance for individual stars, and this would, of course, shift the relationships that we see in Y against Z. And the blue plot is an alternative way of correcting for the parallax offset. So it's definitely true that whatever result we come to in the end will be an enrichment ratio up to the Gaia 0-point parallax offset. And that is something that will have to probably be readdressed in subsequent Gaia data releases. We can see it, basically. So the outlook from this work is that the Gaia luminosities make helium inference possible, not really for individual stars, but with enough stars, we can start to recover the structure in the plot of Y against Z. We're now trying to validate a statistical technique to constrain delta Y against delta Z. The early conclusions would be that probably we don't see multiple tracks in the helium abundance, because from our mock data, we know that if we were to input 2 different sequences in helium abundance, we would be likely to see it as long as they're not too close together. But we're still actively working on this. Once all these many problems are resolved, I'd like to take this method and apply it to red clump stars in the K2 sample, and that would allow us to map helium enrichment around the galaxy, which would be a really nice application and provide very strong and novel constraints on models of galactic formation and evolution. I think I have enough time still to say a couple of other words on thank you on a slightly tangential point related to the Gaia luminosities and the seismology from a different project. So one thing that we have found when working with K2 data, so everything I've previously discussed is about Kepler data, but in the K2 data, if we obtain our stellar parameters, so here is the stellar mass and the stellar radius, in a run of param using what we would normally use, so nu max and delta nu, and the effective temperature and metallicity, we see the expected features. So there's the red clump and the red giant branch bump present here, but we also see a lot of stars in a region where we wouldn't really expect to find them. if we replace the delta nu in our param analysis with the Gaia luminosity, we find that this region is now much emptier. And if we draw lines showing where these stars are going from and to, they basically all really belong in the red clump. So what's going on here is that in short time-based seismology, like K2, and I haven't looked at tests, but I suspect this is the same thing is true, determinations of delta nu can be a bit unstable, particularly for red clump stars. But the Gaia luminosities offer us an opportunity to figure out which ones are affected by this instability and work out where they really belong. And I just thought this was a nice add-on, as I've been talking so much about luminosities and how we use them with seismology. Yeah, I'll return to my conclusion slide now. Thank you very much.
Thank you, Emma, for a very interesting talk. You see people applaud, and I applaud on behalf of the audience. So the floor is open for questions. Please indicate with the raised hands who wants to go with the question. Or simply speak up, open the mic, and Saskia, please. We can't hear you.
No.
In the meantime, there's also a message in the chat. Very nice talk, Emma. Yeah.
Thank you.
Can you hear me now?
Saskia, yes, we hear you.
Yeah.
Okay, great. I can also, so thank you very much for this very nice talk. I just wanted to, it's not a question, but a comment. In 2012, we did some work on testing how long a time series would need to be and how much that impact on your delta nu measure that you have. And so this is maybe something that you could use to also in this last bit that you just discussed.
Yeah, thank you.
Any other questions? In the meantime, I would like to mention that we saw similar things with test data, making the same diagram, not as elaborated as you showed it, but just we found an excess of very high mass targets. And yeah, probably short time data series pipeline, less modes to constrain, and yeah, so
yeah, we've had some
Gaia seems to be.
Yeah, we've had some success in flagging those stars. If you just take the difference in the mass that comes out of your analysis when you use delta nu or the luminosity, you can either take them out or you can correct for them. And it's definitely not a perfect system, but in the project where I'm using the K2 data, which, as I say, is not the one that I've discussed today, that seems to work reasonably well for cleaning things up. So
I think with tests, we even have more 0-point shifts, making that regime more difficult. Jürgen, please.
Thank you for a very nice talk and very interesting results. This is tough.
Thank you.
I just wondered, and maybe I should know the answer myself. Do you know why there's this relation between Y and L on the in the clump?
Yes, I think I have an extra slide. Yeah, so I made a list because it's a bit convoluted. So if you increase the helium abundance, you have two effects. So you're increasing the internal temperature of the star, which would actually lead you to decrease the mass of the core at helium ignition, and yet therefore you would expect a reduction in the luminosity. But what you also do is increase the efficiency of the hydrogen burning in the shell, and because the envelope is so big, that's the thing that really dominates, and that's why you get an increase in the luminosity for an increase in the helium abundance in the clump.
Excellent. There's a very nice paper about the red giant problem by Marcello that came out recently.
Okay.
A simple analysis of this, and it may actually be contained in his analysis, this effect. It might be worth looking for, but I haven't tried.
Thank you very much.
Are there further questions? So do I understand correctly that the luminosity, the tip, remains basically unchanged, even the clump luminosity is changing?
I'm not 100% sure, because we've really only looked at the models after the helium flash has occurred, once you've trimmed out all the pulses and stuff. I would expect the tip, the luminosity at the tip of the red giant branch to change, though, because any process where you're delaying the helium ignition or accelerating the helium ignition, you would change how far you've ascended on the red giant branch. So I would expect it to go up and down more or less in the same way. But I'm not 100% sure about that.
Are there any further questions? Because otherwise, I would like to thank the speaker again. It was a very interesting talk. I learned a lot. And would like to announce the next speaker. On the 15th of February, we have Nuon Alexander Martin Moedas from the University of from Portugal, and he's speaking on investigating the effects of turbulent mixing in F-stars. Everybody is kindly invited. The email and information will be distributed by the usual channels. And yes, with that, I wish you a good morning or a good evening, wherever you are, and have a nice day. Bye.